Good morning. First of all, I want to introduce myself. Myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering. And today my content is GTU question paper solution of the subject of vector calculus and linear algebra of June 2013. So this question paper we already seen up to question number 5b. So let's see question 5c. Verify that the vectors u1 is equal to 1 minus 1 2 minus 1, u2 is equal to minus 2 2 3 2, u3 is equal to 1 2 0 minus 1 and u4 is equal to 1 0 0 1 form an orthogonal basis for R4 with the Euclidean inner product. Also convert it to an orthonormal set by normalizing the vectors. This question was asked in 4 marks in that GTU question paper. So first of all we have to prove that these 4 vectors of R4 are orthogonal, okay, and then we have to convert these 4 vectors into an orthonormal vectors by using by dividing each vector by its norm, okay. So let's see one by one. Basically here we are using Euclidean inner product. So to prove that orthogonal vectors, we have to check each and every 2 pairs of inner product that is equal to 0. So inner product u1 u2, first of all we see inner product u1 u2. So u1 is 1 minus 1 2 minus 1 and u2 is minus 2 2 3 2. So u1 into u2, that is equal to 1 into minus 2 minus 2 plus minus 1 into 2 minus 2 plus 2 into 3 plus 6 plus minus 1 into 2, that is minus 2, that is equal to 0. So minus 2 minus 2 minus 4 plus 6 2 minus 2, that is equal to 0. Then inner product u1 u3. Now next we see inner product u1 u3, that is 1 minus 1 2 minus 1, u3 is 1 2 0 minus 1 1, so 1 into 1 1 plus minus 1 into 2, that is minus 2 plus 2 into 0 0 plus minus 1 into minus 1, that is plus 1, so that is also 0, okay. So inner product u1 u3, that is equal to 0. Next we get inner product u1 u4. Let's see what is inner product u1 u4. In u1 is 1 minus 1 2 minus 1 and u4 is 1 0 0 1. So 1 into 1 1 plus this is 0 minus 1 into 0, then 2 into 0 0 and then minus 1 into 1, that is minus 1. So again we get 1 minus 1, that is equal to 0, okay. So we prove that inner product of u1 with each u2 u3 u4, that is equal to 0. Now next we have to take inner product u2 u3, okay. Inner product u2 u3, that is equal to minus 2 2 3 minus 2 2 into 1 2 0 minus 1. So when you take dot product, minus 2 into 1 minus 2 plus 2 into 2 4 plus 3 into 0 0 and plus 2 into minus 1 minus 2. So this is minus 4 plus 4, that is equal to 0. Then inner product u2 u4. Let's take inner product u2 u4, that is equal to minus 2 2 3 2 1 0 0 1. So minus 2 into 1 minus 2 plus 2 into 0 0 plus 3 into 0 0 plus 2 into 1, that is plus 2. So minus 2 plus 2, that is equal to 0. And then inner product u3 u4, that is equal to 1 2 0 minus 1 into 1 0 0 1. So 1 into 1 1 plus 2 into 0 0 plus 0 into 0 0 plus minus 1 into 1, that is also minus 1. So 1 minus 1 is equal to 0. So here you can see we are proving we prove that all inner product with any 2 vectors of R4, that is equal to 0, okay. And we know that inner product space is commutative. It satisfied the commutative laws. That means inner product u1 u2, that is equal to inner product u2 u1, okay. So that is also 0 we get. So now here we prove that u1 u2 u3 u4 are orthogonal vectors, okay, because taking any inner product of any 2 vectors we get 0. So this all u1, u2, u3, u4 are orthogonal vectors. Now also we have to convert that orthonormal vectors. So for that we have to divide by its norm. So here its norm u1, norm u1, where u1 is 1 minus 1, 2 minus 1. So norm u1 is equal to under root 1 square plus minus 1 square plus 2 square plus minus 1 square, that is equal to under root 7. Norm u2, u2 is what? Minus 2, 2, 3, 2. So norm u2, that is equal to under root minus 2 square plus 2 square plus 3 square plus 2 square, that is equal to under root 21. Okay, so this is 4 plus 4 plus 9 plus 4, so that is 21. Okay, under root 21. Norm u3, u3 is 1, 2, 0, minus 1. So norm u3 is equal to 1 square plus 2 square plus 0 square plus minus 1 square, that is equal to under root 6. Norm u4, u4 is under root 1 square, u4 is 1, 0, 0, 1. So norm u4 is under root 1 square plus 0 square plus 0 square plus 1 square, that is equal to under root 1 plus 1, that is equal to under root 2. So now when we divide by its norm, this is u1 is 1 minus 1, 2 minus 1. So 1 minus 1, 2 minus 1. When we divide by its norm, u1 upon norm u1, that is equal to 1 by under root 7. u1 is 1 minus 1, 2 minus 1, and norm u1 is under root 7. So u1 upon norm u1, that is 1 upon under root 7 minus 1 upon under root 7, 2 by root 7 and minus 1 by root 7. Now what is u2? u2 is minus 2, 2, 3, 2. Okay, and we have to divide u2 by its norm. So norm is under root 21. So u2 by under root u2 by norm u2, that is minus 2 upon under root 21, 2 by root 21, 3 by root 21 and 2 by root 21. Similarly you can see we also write down the u3 upon norm u3 and u4 upon norm u4. u3 upon norm u3 we get 1 by root 6, because what is norm u3? Norm u3 is root 6 and u3 is 1, 2, 0, minus 1. So we get 1 by root 6, 2 by root 6, 0, minus 1 by root 6. And u4 upon norm u4, that is 1 by root 2, 0, 0, 1 by root 2. So in this manner we can write down u1 upon norm u1, u2 upon norm u2, u3 upon norm u3 and u4 upon norm u4. So these four vectors are not just orthogonal vectors, but they are also orthonormal vectors. Okay, they are also orthonormal vectors. So next question 6a. Find the eigenvalues and the basis for the eigenspace of the matrix 0, 0, minus 2. Here we have 3 cross 3 matrix and we have to find the eigenvalues and basis for the eigenspace. So basically eigenvectors, we have to find eigenvectors, and here we have 3 cross 3 matrix. Here is a 0, 0, minus 2, 1, 2, 1, 1, 0, 3. Okay, and this question was asking 5 marks. Here is a solution. Let A be the given matrix. The eigenvalue for A are given by determinant of A minus lambda I, that is equal to 0. So determinant of this matrix, just we have to add in the main diagonal entries, we have to add minus lambda. Okay, determinant of A minus lambda I means we have to add in the main diagonal entries, we have to add minus lambda. So this is minus lambda, this become 2 minus lambda, and here 3 minus lambda. So other entries are same, and we have to find the determinant of that values. So the first row is minus lambda 0 minus 2, next is 1 2 minus lambda 1, then 1 0 3 minus lambda. Determinant of this equal to 0. So when we solve these equations, I hope that you know that how to solve the determinant. Okay, so minus lambda into 2 minus lambda into 3 minus lambda, then this entry is 0, so that will be cancelled out, and then minus 2 into 1 into 0 minus 2 minus lambda into 1, so that will become lambda minus 2, that is equal to 0. Now when we simplify this equation, we get, see, lambda into lambda minus 2, okay, because this minus 1 can be inside in this bracket, so this 2 minus lambda become lambda minus 2, okay. So lambda minus 2 into 3 minus lambda minus 2 into lambda minus 2, that is equal to 0. Now lambda minus 2 will be common from this both the term, so lambda minus 2 in bracket, what will get, lambda into 3 minus lambda, so that will become 3 lambda minus lambda square minus 2, okay, because lambda minus 2 is already we are taking common from this 2 term, so lambda minus 2, and the other terms are in this bracket, that is 3 lambda minus lambda square minus 2, okay, that is equal to 0. So lambda minus 2, now multiply this bracket by minus 1, and right hand side already we have 0, so there is nothing affected on the right hand side. Lambda square minus 3 lambda plus 2, that is equal to 0, and when we factor this 2 degree polynomial, that will lambda minus 2 lambda minus 1, so lambda minus 2 square into lambda minus 1, that is equal to 0. So the eigenvalues of A are 1, 2, 2, okay. So the eigenvalues of A are, you can see from this equation, lambda minus 1 is equal to 0, so lambda is equal to 1, and lambda minus 2 square is equal to 0, so lambda is equal to 2, but 2 occur in 2 times, okay. So the eigenvalues are of A are 1, 2, 2. Now also we have to find eigenvector corresponding to eigenvalues. So first of all we are finding eigenvector corresponding to lambda is equal to 1, okay, and then lambda is equal to 2. So an eigenvector x, that is equal to x1, x2, x3, corresponding to an eigenvalue lambda is given by a minus lambda I into x, that is equal to 0. Now what is a minus lambda I? Here is the matrix, right? You can see this is our a minus lambda I, this determinant. From this determinant you can write down the matrix. Minus lambda, first row is minus lambda 0 minus 2, second row is 1 2 minus lambda 1, and the third row is 1 0 3 minus lambda. So minus lambda 0 minus 2, 1 2 minus lambda 1, 1 0 3 minus lambda, and this is x is from x1, x2, x3, and that is equal to 0 0 0. So here is our main equation, and now we are finding the eigenvector corresponding to lambda is equal to 1. So put lambda is equal to 1 in this equation 1, okay. So when lambda is equal to 1, this equation 1 becomes, now you can see from this equation, this is minus 1 0 minus 2 1 1 1 and 1 0 2, okay, minus 1 0 minus 2 1 1 1 1 0 2, right. This is x1, x2, x3, that is equal to 0 0 0. So we put lambda is equal to 1 in this equation 1, okay. So we get this matrix. Now we have to convert this matrix into a row echelon form. Now what is the meaning of row echelon form? Row echelon form or reduced row echelon form, that you should know, but again I repeat that what is the meaning of row echelon form. So if there is any matrix, there are some conditions to be satisfied to become a row echelon form matrix. The first condition is if there is any 0 row, it should be the bottom of the matrix, right? That is the first condition. The second condition is our leading entry. Leading entry means we are starting from left to right in any row. The first non-zero element that we call leading entry, or sometime we call pivot, okay. So from leading entry in any column, below that leading entry all the elements should be 0, okay. In that column below that leading entry all the element should be 0 in that column. And the third condition, whenever we are going from above to below, our leading entry is going from left to right in a matrix, right. So if these three conditions are satisfied, then we can say that our matrix is in row echelon form. And to become a reduced row echelon form, two more conditions we have to add. The first one is our leading entry must be 1, right. Leading entry must be 1, And the second condition is, in that column, in which column we have leading entry, definitely we have below that leading entry, in that column we have 0, but above that leading entry, right, above that leading entry also we have to, also we want 0, okay, there. So basically in reduced row echelon form, in the column in which we have leading entry, except that leading entry all the elements should be 0, except that leading entry all the elements should be 0, either it's below or above, all the elements should be 0. So if these three conditions, the first three conditions are for row echelon form, and the another two conditions, so total 5 conditions are for reduced row echelon form, okay. So here we have to convert this matrix into just and only a row echelon form, and using that row echelon form matrix we can solve the equations, we can solve this, the value of the matrix x1, x2, x3, okay. So minus 1 0 minus 2 1 1 1 1 0 minus 2. First of all we are this is our leading entry. So what we are doing here, we are multiplying first row with 1 and add into the third row, okay. So the first row and second row are as it is, minus 1 0 minus 2 1 1 1, the third row become 0 0 0, okay. Now next we are multiplying first row with 1 and add into the second row. So minus 1 0 minus 2, the first row is as it is, the second row is 0 1 minus 1 and 0 0 0. This is x1, x2, x3, that is equal to 0 0 0. So now you can see this matrix is in row echelon form. This is our leading entry, below that leading entry we have 0. In second row this is our leading entry, below that leading entry we already have 0 now, okay. So next so this is our matrix which is in row echelon form, minus x1 minus 2x2 that is equal to 0, minus x1 minus 2x2 that is equal to 0, and then x2 minus x3 that is equal to 0, x2 minus x3 that is equal to 0. So in which column we does not have any leading entry? The third column, you can see the third column we don't have any leading entry, so that's why we are taking x3 is equal to t, corresponding to x3 is equal to t.